This is a demonstration of Innovative Integration's X6-GSPS XMC module loaded with spectral analysis firmware. The firmware resides on a Xilinx Vertex 6 FPGA located on the X6-GSPS module. The firmware consists of standard framework logic supporting the spectral analysis firmware of the implementation. An analog input from 30 to 512 MHz is assumed for this implementation, and 12-bit digitization is provided by the onboard ADD converters. In this implementation, a sample rate of 1.6 gigasamples per second is selected. Data is packetized and routed to the spectral analysis firmware. Output data is repacketized and rerouted to the PCIe bus interface module, which then transmits the data to the host PC. The spectral analysis firmware itself consists of a complex down conversion centering the input bandwidth at baseband. A decimating low-pass filter follows with an output sample rate 1/2 the input sample rate, or in this case 819 megasamples per second. Input buffering and windowing is provided prior to the 32K point FFT. Magnitudes of the complex FFT outputs are calculated and bin filtering is provided. In this implementation, 132K point FFT is provided every 30 microseconds, and at that rate a full spectrum report would quickly overwhelm the PCIe interface. For that reason, a full spectrum reporting method is provided, but the user is expected to use manual single triggering captures. A second reporting method is provided, which allows more contiguous monitoring based on threshold limits. In this mode, the user supplies bin thresholds for each of the 32K bins, and only bins exceeding their threshold are reported across the PCIe bus. The number of bins is limited to 512 in this operating mode. Spectral processing is as follows. An external anti-aliasing filter is expected to condition the input bandwidth. The input bandwidth is digitized and then down converted to baseband. Following the down conversion to baseband, the decimating low-pass filter provides image suppression and image attenuation greater than 65 dB for the portion of the image which will alias back into the passband. For this demonstration, we will show both full spectrum reporting as well as threshold limited spectral reporting. The equipment required is an X6-GSPS module inserted onto a PCI Express carrier card, which allows it to be installed in a Windows PC. For the full spectrum reporting, we will use an input signal consisting of an FM modulated 250 MHz carrier. The sample clock will be chosen to be 1.6 GHz and generated by the X6-GSPS phase lock loop. For best frequency accuracy and resolution, the signal generator's 10 MHz output reference is used as the clock reference for the onboard PLL. For the spectral analysis firmware application, a customized snap example was created. After opening the API, the X6-GSPS module is opened. The software reports on the status and shows the PCIe Express bus configuration. Next, clocks are set up. Again, we are using an external 10 MHz reference from the signal generator, and we're using the internal or onboard phase lock loop to provide the sample clock. at a rate of 1638.4 megahertz. We request a full spectrum report and single frame triggering. We select a data source from the A to D converter, and the tuning frequency for the quadrature down converter is set to 271 megahertz. We begin data streaming, and for the first frame, I'm going to turn the FM modulation off. I select the trigger to capture a frame and note that it is captured, and then I'm going to turn the FM modulation on. After that, I'm going to capture a second frame, and finally we're going to turn the carrier frequency to 400 megahertz. And capture a final frame. I close down the default plotting data because this particular implementation requires very low latency. Therefore, the FFT outputs are not provided in natural order, and instead frequency bins are output in bit reversed order. To view a plot of the data, some post-processing is required. We select the default logging file and give a name for the processed file that we want. A full spectrum report is indicated. In the local directory, two new binary files are generated. One of them contains the reordered frequency data in the original data output format of 16 bits scaled volts. The second is given in units of dB. Opening up the dB file, we can look at the first frame of FFT data. The plotting software being used expects time domain data, so please ignore the access labels. In this demo, the x-axis is a frequency bin number. And so you can see from 0 to 32,768 samples are provided. Scaling the data, we can get megahertz to be shown, although the units aren't correct. So in this first frame, the carrier is shown at 250 megahertz. You also see the second harmonic, which is output from the signal generator at 500 megahertz. The image frequency of the carrier is shown here, and because it's outside the band of interest, it only has about 45 dB of attenuation. The next frame shows the carrier with FM modulation enabled. And the third frame contains the switch to 400 megahertz as the FM carrier. So again, going back to the first frame, 250 megahertz carrier. Second frame, modulation turned on. Third frame, we switch to a 400 megahertz carrier. For the threshold limited reporting demonstration, we will use an input signal consisting of a frequency stepped sinusoid, which starts at 50 megahertz and steps by 50 megahertz every 100 microseconds, up to a frequency of 500 megahertz, looping continuously. The signal generator's output amplitude is set to decrease from a maximum of 0 dBm at 50 megahertz down to negative 50 dBm at 500 megahertz. The clock configuration will remain the same. Going back to the software API, we confirm the clock configuration. And on the analysis tab, we want to make sure we now select threshold limited spectrum with continuous triggering. We start data streaming and observe that because of the continuous triggering, data is continuously transferred to the PC host. We stop the capture and again post-process the log file for threshold limited spectrum. Two new binary files appear and we open up the DB file and set the span for the full FFT range. Noting here that the 50 megahertz signal is in the first frame, and as we page through frames, we see it step to new frequencies. Also note the amplitude is decreasing as the frequency is increasing. Stepping back through the frames, we can capture a jump in the middle of this frame. And that concludes the demonstration of the spectral analysis firmware.